Hello, in this video, we're going to talk about an idea known as the comparison theorem / test. We're going to use the comparison theorem a lot in a later section. So we're introducing the idea now with integrals, but we'll see it in another form in a couple sections. So suppose I have functions f and g. So I have f is going to be in blue, and g is going to be in red, where f of x is always bigger than g of x, or possibly equal, for all values some point a onward. Then, if I have it such that the function f of x is integral converges, so that means the integral from a to infinity of f of x dx comes out to be some number. That's what it means to converge. Then what we're saying is the area under this curve equals out to some number. G of x has a smaller area. It is wedged between f of x and the x-axis. There is no way to suddenly have an infinite amount of area if it's always smaller than f of x. So if the function f of x converges, this means the function g of x. That integral also must converge. And then if g of x diverges, meaning we don't know what this area is, it's an infinite area, or somehow the limit does not exist in another way. Most often, the limit is infinite. So most often, we'd have the limit of g of x dx equals infinity. Well, if that area is infinite and f of x is adding on more area, then the integral of f of x has to also diverge. So if the small diverges, then the big diverges. And if the big converges, then the small converges. Warning, if we have these things switched, we don't necessarily know about the other. So if I know the big thing converges, I don't know about the small, because my functions f of x and g of x would be not compared to each other at all. F of x would be some function that grows, and g of x could basically just follow the x-axis. Just because we know something about that f of x does not mean I can say something about g of x. So if f of x diverges, then we know nothing about the integral of g of x without trying to evaluate that integral. And if g of x converges, well then, our small thing, it could just be the zero function. If the zero function has an integral that converges, I know nothing about any other function that's bigger than that. So if the small function has an integral that converges, then we know nothing about the integral of the bigger function. So that is the comparison test, and we're going to take a look at an example of how this works. Suppose we're looking at this function 1 to infinity of x minus 3 over x to the fourth plus 2. We could pull out the strategies from We could pull out the strategies from partial fraction decomposition and try and work this out. However, x to the fourth plus 2, not super easily factorable right off the bat. So I just want to know, is it convergent or divergent? And I want to know that as quickly as possible. I want to know, does this come out to a number? Well, I do know that the integral of 1 to infinity of 1 over x to the p converges if p is greater than 1. If I can compare x minus 3 over x to the fourth plus 2 to 1 over x to some number p, I can try and use this comparison test. So I'm going to see if I can simplify this down. Well, if I'm subtracting 3 from something, that is going to be bigger than something where I'm not subtracting 3. Right? 5 minus 3. Sorry. Wrote that backwards. 5 minus 3 is going to be smaller than 5. 6 minus 3, smaller than 6. -5 minus 3 is smaller than -5. Now, if I can get rid of this 2 some way, and we also know the bigger a denominator is, the smaller the whole fraction is. So without changing that numerator, removing this 2, I make the fraction smaller or bigger by removing the 2. And this is 1 over x. That should be a fourth there, so that is a 3. That means I know this function, x minus 3 over x to the fourth plus 2, is a smaller function than 1 over x cubed. However, I do know, again, the integral from 1 to infinity of 1 over x cubed dx converges by the p-series test for integrals. We worked that out earlier, actually. We already have evaluated that integral. By the comparison test, we know that if the bigger integral converges, right? If f of x converges, where f of x is bigger than g of x, then the integral of g of x converges. Therefore, the integral 1 to infinity x minus 3 over x to the fourth plus 2 converges by the comparison test. What number does it converge to? I'm not sure. I do know this integral came out to be 1/2. So it's going to be smaller than 1/2. What is it exactly? We don't know. We need more work to figure that out. But we at least know there is a number, it would converge. So we have the integral test, or the p-series test for integrals, showing us there is convergence of this integral.